Hi everyone. So I'm going to go over a project I recently completed. This is a clock that I made. I etched this top board here myself at home. It's just a sheet of copper clad. I printed out a mask. I developed the mask and did the photoresist and all that type of stuff, and used the ferrochloride to etch away the copper. I've done this many times before, and I actually ran out of single-sided copper clad, so for this time I used a double-sided piece of copper clad, and I just put tape on the back of the board so that it wouldn't be developed. But you can see here the piece of the tape kind of peeled back, and some of the ferrochloride got underneath. You can also see over here there's some etching that both the tape also got peeled back. So that's one thing I wish I did differently. I wish I had a piece of copper clad, single-sided copper clad that was big enough for this cut. But one of the whole points of this project was to use materials only on hand, and not buy a single thing. So I have a spool of these WS28B LEDs from World Semi. I also have a spool of the tinier ones, the WS2812B mini. So these are 5mm by 5mm. The smaller ones are 3.5 by 3.5. And I think currently, halfway through 2020, the only place you can buy these LEDs from the factory is this is a JLC, whatever. What would it be called? But through JLC, through the component store. And then here, my little kickstand. That's all it is. It's just a kickstand. I used I'm sorry about that. AVR to ARM adapter. So this is a little board I made to. So I have two of these AVR J tags, and they're the ICE 3s, and of course the pins on here, you go through that alpha cable, which flips the cable twice and puts the connector backwards, so it's not pin 1 to pin 1 through the cable. And then on the other end of this cable, you get an AVR type of 10-pin J tag. And then if you want to plug that into a standard ARM device, you need to swap those pins again, which is why I made this PCB, is to go from one end of the cable that plugs into here into a standard 10-pin ARM header. These PCBs over here, I just had laying in a box. I have a box full of old PCBs that I've created, and I'm using this one on the left just to get a micro USB. And then over here I have a ATtiny85. I also have a couple pull-ups, a bypass capacitor, a programming port, and that's about it. This board here, I wanted a way to be able to unplug the DS3231 chip. So I didn't want to solder it on directly, so I put this board in just because it had the right it had 6 pins or something, and then 6 pins on the other side. So this is just a board, so I didn't have to solder these wires directly on there, and I could get this header on nicely. Then snaking around the back of this, inside here, I have my JTAG programming port. And that cable, you just give me 1 second, plugs into the JTAG. Excuse me while I plug it in. Oops. And just like that, my JTAG is plugged in. So, and then back here in the corner, these are actually on my vias. So one thing nice about having the double-sided port is that this back plane here is actually all ground, which helps with some noise stuff, which I'm not too worried about. And then it also gives me the ability just to drill holes through here and kind of plate them with solder, which allows me to not need any wires coming from the front side around the corner to the back, and it all kind of just goes right through the PCB. And then I also had to put some jumpers in here, so you can see here's a point where I have to jump from here to here, here to there, there to there, all the way over, and down there are some more jumpers. And for that I just used little pieces of wire. I tried to bend them into a nice shape, and some of them look pretty good. Those two I think look pretty good. That one's a bit flat, that's okay. And then some of them are kind of ugly shape, like those. When I was making the PCB in KiCad and doing my layout, it was a really quick and extremely dirty layout, and I actually forgot to connect that pin to that pin right there. So I had to come back in and put that in myself. You can see that this piece of copper is starting to tarnish as well. You can kind of see some of the chemical residue here, but I got an old can of clear paint, and I try to put a layer of just clear coat over it to stop the tarnish. And this is my first time attempting to do that, and it did not work one bit. So maybe the spray paint was not the right type. Maybe I need to get a special type of clear coat, excuse me, to really lock in that copper look and prevent tarnish. Anyway, we can plug it in. So the power for this is just a micro USB. It just gets plugged in. Oh, come on. Okay, it's plugged in. And so right now the brightness is extremely low compared to the maximum capabilities. Let me get this set up. And I can there's a few things I want to show. I guess I'm going to start with some software stuff, and then I'll go into some of the signals on the PCB. I guess before we do that, we can also come down here. Here's a little USB meter. So it's saying it's taking about 80 milliamps, which is what's 80 times 0.5, 0.08 times 5. Oh, I'm in programming mode. 0.08 times 5. A little bit less than half a watt, which isn't too bad to keep it always running. I think that is a lot higher than some other clocks would use for sure. But again, these little USB meters, they don't do too good at low current, measuring low currents like this. So anyway, here's my Atmel project. It was all done in Atmel Studio. Again, I'm using an ATtiny. It's actually an ATtiny85. I first tried to write the code for a ATmega328B, but I remembered that the internal clock on the PCB can only go up to 8 megahertz, while the internal clock for the ATtiny, there's a phase lock loop option which allows you to go up to 16 megahertz. And for driving the WS28 LEDs, it was a bit easier to do it at 16 megahertz rather than 8 megahertz, given the 1.25 microsecond period drive for the LEDs. So in the beginning here, I include some libraries for the LEDs and an I2C master. I define the address of the RTC module. I define some pixels, set some matrices, some vectors for the output. And actually, thought I wasn't using this. Anyway, I might need to go back and delete that. Maybe it's getting optimized out. I think it's getting optimized out. Nope, let's focus. Focus, you fuck. Okay, so in the beginning, I set up some values here. So if you see, I'm doing an HSV color scheme. Oh my god. And right now I have the value set to 10. So that means I'm running at 10 divided by 255. 4% of total brightness. So, and at nighttime that is actually quite bright. Focus. Okay, so anyway, if you go down, here's where I do some converting from 24 hours to like a 12-hour standard for the clock. And here I do the subtraction for 12 if it's over that. Here is one where I go from midnight time to like 12 in the morning type of thing. And here is a blank character. Instead of putting a leading 0, I put a blank character in. So, stay focused. I guess one function we can take a look at very quick is the, come on. So here's my get time function. So basically you start up the I2C and you want to read address 00 from the RTC module. So to do that, you first start the transfer at address 80. You write what address you want to read. You do the write for what you want to do that, and then down here we actually read a byte back. And when we read the byte back, I'm actually getting a bunch of information in there. So we want to mask it, and this is where we get the seconds, which we used to blink the colon, which is why that's called colon. Down here we get the minutes. So this is the first digit of the minute, or this is like the ones digit for the minute, and this is the 2 digits for the minute. And you can see you get different bits here. So the first 4 bits is the 1 digit, next 3 is the 4 digit. The tens digit. Excuse me. And the thing for the hour is almost identical as the minute, except you're going to address 2 instead of address 1. So that's all that, and I got the scope out so we can give this a quick probe. So when we're probing this, I'm going to take one lead across SDA. Nope, I'm sorry, you can't see this too easily. So I'm going to pull out the module a tiny bit. There's a clock. Oh, you can't even see it either. And there's that. Okay. Now the last thing we need is the ground, which I'm actually going to stick over here. Okay, so now we've got both probes hooked up. We're going to enable them both. And we got a trigger on something. And here we see some data. So I'm going to put decode option on, I2C decode on. Let's do a single shot. Let's exchange that. Go over here, single shot. So again, in the code, we can see we first write the address here, which is D0. Then we say what address do we want to read, 00. Then we do a read for D0, which you then do the last bit becomes a write bit. So that becomes D1, and it's saying, oh, the entire message is 17. So that's it for that. If we go over, 17D. Okay, so here's where let me zoom out actually. Let's try to get the list. So here's the thing of tables for this. So we write to it a 00, then we read from it a 58, and that's the seconds. We write to it a 01, we read to it a 35, and this column here is I think it's hexadecimal. I believe it is. Yeah, it's definitely hexadecimal, yeah. So anyway, so 00, that's seconds, 01 is minutes, 02 is hours, and then we have to decode this information and bit shift it appropriately. Anyway, so we can see it, it's still running. There's a change in the time. And that's just the I2C transfer. So for each time the display updates, it does something, it does something, of course it does. So first we update the color fill. So basically what I first do is update all the pictures with a color palette. And this color palette, is constantly changing little by little. So that's update color fill, and then I wait a little bit just to kill some time. And then I get the current time. I change the digits. So in get current time, I update digit 1, 0, 1, 2, and 3. And then I fix, because when I get them, they're in a 12-hour format. They're in a 24-hour format, and then I convert them to 12 hours. And I do that with 3 if statements here. And then I apply the bit mask over it. So if we go down to here to apply digit mask. So here's where I turn off the LEDs I don't want on. And that's how you kind of read out the digits. And then I just send out the data. And that's basically it for this project. I wanted to kind of document it a little bit. And yeah. And I'll show you, you can just hit the program button. It's going to yell at you for something, and then I click it. We went back to hue 0, and that's it. I hope you enjoyed the overview of this project. Thank you. Bye bye.